This section we're going to look at optimizing different situations, and this shouldn't be anything new. We're going to take an old idea that we studied with quadratics and now bring the world of calculus into it so that we can analyze functions other than quadratics that model the world around us. So for optimization problems, we're going to assign variables. So if we're going to use x and y, we should say what x and y mean, or whatever variables we're using. And when possible, draw that sketch. Visualizing the problem on paper can be really helpful in determining the equations that you need to write. So we're going to try to write an equation that we want to optimize. In other words, that we want to maximize or minimize. And we want to get that equation written in terms of only two variables. For instance, area equals not length times width, because that would be three variables, but only two. And what we're going to do is we're going to find values that are sensible or feasible for the problem situation where the derivative is equal to 0. We've looked many times throughout this section that maximums and minimums occur when the first derivative is 0, and we're going to verify that we have a maximum or minimum using either the first or second derivative test. And if we have a domain for possible values of x, so x has to be between these numbers, we have to actually test the endpoints to make sure that the maximum or minimum isn't happening at one of those values, because it's possible that we could have a graph or a function that looks like that, or I guess like this, and this would be a minimum, but if this is the biggest number that we're allowed to use, that's actually the minimum value that the problem can be for that particular situation. So you need to be aware of that as you're working and conscious of that in these problems. So here's our first example. The sum of two positive numbers is 48. Find the two numbers so that the sum of the first and 3 times the second is a minimum. So let's let x equal first number and y equal second number. These variables weren't in the problem, so we need to make sure that we're defining them before we go any further. And we're also talking about the sum. So s equals the sum of numbers. And that's what we're trying to minimize, so I want to write an equation for that. S equals, well, what are we adding together? We're adding the first one, so x plus 3 times the second. But here's a problem, guys. That has 3 variables. I want an equation to minimize that only has 2 variables. So I hope there's more information in this problem, and there is. Except I used the wrong word here. This is not supposed to be the sum of 2 numbers. It's supposed to be the product. We could do it, but this makes the problem more interesting. The product of 2 positive numbers is 48, so x times y equals 48. Now, how can we use this information to get this s equation into just 2 variables? Well, we can make a substitution. We could say that y is equal to 48 over x. So s is equal to x plus 3 times 48 over x, or s equals x plus 144 over x. Now write that as x to the negative first. Now we have a function in 2 variables. S equals something involving x. So this is something we can differentiate. S prime of x. So it's going to be 1 minus 144 over x squared. And if I'm looking for the max or min, we're setting this equal to 0. We end up x squared equals 144. So x is plus or minus 12, but we're told the 2 numbers are positive, so x is going to be 12. Now, how do we determine and how do we make sure that this is indeed a minimum? Well, I'm going to use first derivative test. 0 is the minimum that it can be. the numbers could be as large as possible. So there is no endpoint of this interval to check. Here's my 12 where the derivative is equal to 0. Let's try s prime of 1. S prime of 1 is going to be less than 0. So s is decreasing. S prime of 13 is going to be greater than 0. So s is increasing. Therefore, x equals 12 gives a minimum for the sum. And what are the two numbers? Well, they're 12 and whatever 48 divided by 12 is, which I'm getting from right there. So my other number is x equals 4. That should be y equals. So there we go. There's calculus at work, minimizing a situation that we came up with a model for. Example 2. Now we're dealing with a plot of farmland. We have 180 meters of fencing material, and it's a rectangle. On one side, the fourth side, this plot is bordered by a stone wall. So we have this grassy field. It's a beautiful field, isn't it? And it's bordered over here by a stone wall, which means our fencing is going to go on that side, and that side. We want to find the dimensions of the plot that maximize the area, and we want to find that area. So area is what we're maximizing. Area equals length times width, or base times height, or however you want to call it. But again, 3 variables. I don't want 3 variables. We need more information, and we have more information, this 180 meters. That 180 needs to be W plus 2L, adding up the 3 sides of this enclosure. That has to equal to our 180. And we can rearrange this, and we can say that W equals 180 minus 2L, and that can be substituted over here for A. A equals L times 180 minus 2L, and we can distribute. So this is now, A is now a function of L, and it's 180L minus 2L squared. Now we can take the derivative with respect to L. It doesn't always have to be with respect to X, remember. This is just a variable. We could have very easily defined X and Y as the length and width. But I defined W to be the width and L to be the length. So my derivative is 180 minus 4L. Now if we're optimizing this, this needs to be 0. So L is equal to 45. And when L is 45, W is going to be 180 minus 2 times 45, or 90. But we need to make sure this is indeed giving us a maximum area. And to do this, I'm going to use the second derivative test. In other words, I'm going to look at the concavity of this function at L equals 45. So a double prime of L will be -4, which is less than 0, which means that A of L is concave down, and L equals 45 is a maximum for area. Okay, so the dimensions are 45 by 90, and our actual area would be, well, 45 times 90, which is 4050 square meters. And really, I should go back and look at my interval. L, so here's my 45. The smallest L can be is 0. The biggest that L could ever be is 180. Well, if L is 0, we don't have a pen. The width would be 180. No, we wouldn't. These two sides wouldn't exist. And same thing if L was 180, then we wouldn't have a pen either. So our maximum, our optimization can't occur at the endpoints of the feasible values for L. So my answer is simply the pen should be 45 by 90 with a maximum area of 4,050 square meters. And that's where I leave you, ladies and gentlemen. Remember that first thing that I showed you, those steps to follow. Draw that picture, write the equations, then use the beauty of calculus to find an answer.